Hey everybody, welcome and thanks for joining me. And in this video, I'd like to talk about limits and continuity. Now, limits are a useful tool for reasoning about function behavior. And I'm assuming you've been exposed to functions at this point. You probably know what they are if you're thinking about limits and continuity. But put simply, a function is just an algebraic equation that attempts to model some system or phenomenon that you're studying. And for any given input, usually denoted by the letter x, will give rise to a specific output. Now, limits are useful for analyzing continuous variables, such as weight, the distance between two objects, temperature, even time is considered a continuous variable, and there are many, many more. But for example, you can stand on a scale that might read you weigh 129.3 pounds. But that is only because as humans, we don't need additional precision to make an informed decision about our body weight. But in reality, you will weigh 129.3, let's say 4563998576112, and so on for an infinite number of digits after that decimal place. That's what's really happening, and that's what you actually weigh. But it's only useful to go one place after the decimal when making a decision. And another continuous variable is time, which we can measure down to milliseconds or microseconds, even nano or picoseconds, and so on forever. It doesn't end at any particular value. There is no cutoff. We can compare this to discrete variables like the number of people in a room or the score in a football game, for example, where the variable can take on an exact value. It doesn't have to deal with, or you don't have to contemplate infinity. For example, there can be one person in the room. There can be exactly two people in a room. You could score exactly 7 points at a football game. Or you could score exactly 28 points in a football game. The big difference between these two types of variables is whether or not you have to contemplate infinity. Now, as you move into different scientific domains, such as quantum mechanics and physics, or molecular biology and astrophysics, stronger levels of precision when dealing with continuous variables might be required, and that's where limits come in handy. They also come in handy when thinking about discontinuities and where they might arise. And a discontinuity, depending on what you're studying, finance, engineering, statistics, whatever it might be, it could be anything, could have significant ramifications for your description of whatever you're trying to study. So with that, let's use a single equation to try and capture as many operational elements of limits and continuity as we can. Okay, so we have our equation here, our function, f of x, and the first thing you would do when thinking about limits is direct substitution. Now the notation for a limit will look like this. So we'll have this term lim here, which means limit, and we want to find the limit as x approaches some value c for the function f of x. And so the limit, the value we want to find the limit of, will be 2. So we will take the limit. We want to know the limit as x approaches 2 for the function f of x. And so this will just translate to f of 2. Because we are inputting the x value, direct substitution. We are inputting 2 into the function. And so what value do we get? We get 2 squared plus 1 over 2 plus 3 times 2 minus 1 squared. And this adds up to 4 plus 1, which is 5. 5 times 1 squared, which is just 1, so 5. And so our answer is 1. And what this is telling us is that the function is approaching the value of 1 as you move from the left and the right. And so this limit exists, and it is 1. Now I chose a rational expression, as we can see here, for a reason, because I wanted something to be in the denominator to showcase what a discontinuity looks like. And so let's take the limit, and I did it in a different color here. Let's take the limit as x approaches 1 of the function f of x. Now if we evaluate this, we get 1 squared plus 1 all over 1 plus 3 times 1 minus 1 squared. And this equals 1 squared is 1, plus 1 is 2. 1 plus 3 is 4. 4 times 1 minus 1 is 0. 0 times anything is 0. 0 squared is also 0. So this is what we get if we plug in 1 as our input. And as we can see, having a 0 in the denominator makes it undefined. When we have something that's undefined, there is potential that the limit does not exist. It's also possible we have a vertical asymptote where a limit does exist, but that limit is infinity or negative infinity. And so let's look at a way we can determine whether or not it's a vertical asymptote or just the limit doesn't exist. Now that we know that the limit as x approaches 1 for this function is undefined, we can use a technique called input tables to get a better understanding of what is happening at this limit. And in an input table, we will take any value that gets closer and closer to 1 from the left or the negative side of 1. So we can do 0.99 and put that into the function. Then we can do 0.999 and then 0.999 and so on. And you can do this forever if you wanted to. But this should be adequate to determine what value is this function approaching as we get closer and closer to 1. And then this is denoted by, we can denote this by, let's put it right here. The limit as x approaches 1, but from the left for f of x. So this negative sign indicates that we are approaching 1 from the left, or any negative values, or any values smaller than 1. And then we will do the same thing on the right, or any value that's larger than 1. So we take the limit as x approaches 1 from the right, which is notated by this positive sign. And so let me make an input table, which we can look like that. And so 1.01 is pretty close to 1. 1.0001 is even closer, and 1.001. Okay, let's just make this 1.01. Okay, and instead of having you guys watch me do the calculations, I will just evaluate these and give them to you. Okay, and so here we have the values after evaluating for each input, and we can see that as we get closer and closer to 1 from the left, we are getting closer and closer to the 5. And it's pretty obvious, 96, 99, 999. And the same thing is happening from the right. So any value greater than 1 as we get closer and closer to 1 is getting closer and closer to 5. So we could say that this limit does exist. And in fact, it is a vertical asymptote. And up to this point, I wanted to avoid showing graphs because it makes it a little bit easier than it really is when we think about it from an algebraic perspective. You can get lazy when just looking at graphs. But as x approaches 1 right here, we have a vertical asymptote. which just means we'll have this dashed line. And as x approaches 1 from the right, it will look something like this, the function will. And as we approach it from the left, it will also look just like that. And these function values, so the outputs, will never ever touch this line, but it will get closer and closer and closer. And that is a vertical asymptote, and that is represented by this equation. So now that we are introduced to infinity, let's think more about it and think more deeply about it and do a problem using the same equation, but now we will think about infinity. So now that you've been exposed and seen how infinity might work in limits, let's think about it even more. So let's find the limit of the function f of x as x approaches infinity. And in order to do this, I had to rewrite the same equation. So all I did was combine these two terms in the denominator so that it's expressed in this form. And this is necessary so that we can see the highest degree terms. Because when we think about infinity, all we care about is what is happening at very, very, very large numbers and very, very small numbers. And so our leading terms here are x squared and x to the third. And so they have the overwhelming impact and influence on the equation. So we can see it as x squared over x cubed. And so if we plug in infinity into these two terms, which by the way, this can be simplified to 1 over x. And so if we plug in infinity into this x value, so we're thinking about the largest number possible, we are becoming, this equation output is getting infinitely smaller. So we are approaching 0. So the answer to this question is 0. The limit as we approach infinity for this function is 0. Now imagine these two terms were flipped and we had a different equation. We would see that it would be x over 1 and we would be approaching infinity. Because we would plug infinity into this x value, it'd be over 1. This is the largest number possible. So the answer would be infinity. This would be infinity. Whoops. We could also do the limit of f of x as x approaches negative infinity. And let's plug it into the actual equation. So we have 1 over negative infinity. And so this number is getting infinitely closer and closer to 0. Now that we've done all of the major operations with limits from an algebraic perspective, we can now look at the graph of this function. So now we can see here the graphical structure of this equation that we've been dealing with this whole time. So all of the algebraic work we've done up to this point can be represented in a visual form like this. So we can see that as x approaches 1, which we were doing in our equations, we are getting closer and closer from both sides to the value 5. And so this is unbounded to positive infinity. The limit does exist for this one. But we can see over here on the left side, which we didn't do algebraically, that negative 3 is a input value that doesn't have a limit. It doesn't exist because we are approaching the same value from the left differently than we are approaching that same value from the right. And so it is considered to be non-existent, that limit. We are unbounded to negative infinity and unbounded to positive infinity. And so therefore we can't have two different values approaching the same value. The function at this point, this specific value doesn't exist. And so that's a great summary of limits and continuity, a great primer to it. Obviously, there's more you could study, more you could learn. There's more nuances, you can do more problems. And that's going to be the case with any topic. And maybe you'll advance our understanding after learning this and as you move forward in your educational and academic journey. So with that, we'll see you in the next one.